right, let's do this. Okay, I don't need slides. Because it's all set up in the 11 a.m. As you know, we're doing live coding. This is our strategy, is live coding. I do want to go to the course website real quick. So we're doing unit testing today, of course. That's our whole goal. And just a reminder, the deadlines come very, very fast. The expected deadline for this task 1, which we're finishing up the content for today, the deadlines are always 2 days after the content is finished for that assignment. So task 1 officially assigned today, technically, but you, as I said before, you should have gotten a start on it. And then Thursday morning, this is 8 a.m. Eastern, all times Eastern Standard Time, 8 a.m. So really you have today and tomorrow to finish task 1. Now I was looking, I guess I can get updated stats for y'all. I was looking at the stats, and a lot of y'all did take my advice to start this early, so I'm very happy to see that. I don't like seeing anybody fail, and missing these expected deadlines and starting to rely on the final deadlines is a sure way to fail, especially in the summer class. So just to share some stats, I think 2 of us are TAs, so I got to do a little bit of math here. 27 of y'all are already done with the assignment. It's out of 58 total, so we're already past halfway. So a lot of y'all did get ahead of things, so I'm happy to see that. Those of you who haven't, how am I wording this? There are another 3 that have started it who haven't finished, who have made a submission that haven't finished the assignment yet, who are still working on it. So those of you, I'm glad you got a good start on it, a head start. To the, oh my goodness, I can't do math today, 28. To the 28 of you, oh, so we're not even halfway yet, are we? Yeah, we're not quite halfway. 1 more of you, and then we'll get halfway. To the 28 of you who did not even, no, my math is wrong here. No, yeah, that's right. Yeah, so we're not quite halfway. So to the 28 of you who didn't start the assignment yet, I urge you to please get started. I don't, I say please, but really it is for your own good. I mean, my day, my summer goes on just the same, whether you pass or fail the course, for better or worse, but I don't want to see you fail the course. You've got to get started on these. Now, you might be waiting for the actual official content this summer. Maybe you didn't want to watch the old videos. That's fine. Make sure you are aiming for this expected deadline, though. Do not rely on those final deadlines. That's an easy way to fail the class. So with that, let's talk about unit testing and talk about the rest of the stuff you need for that assignment. And I think I want to do it this way again. I'm going to do a lecture package. That's what I did last time, yep. And I'm going to duplicate a lot of the stuff that you're going to see in the sidebar here. I'll leave this here so I can kind of use it as a reference for myself. But let's create a new class. I'm going to call it the same thing, adder. And I want to write a method. This method, I'll do JavaDoc style again. And I'll write this in the way that I would have it if it were an assignment on a task. I'll write it that same way. So write a method named add5 that takes an int and returns the input plus 5 as an int. I'm thinking about the way I would word it exactly. This is pretty close. Maybe I'd clean it up a little, maybe not. But it takes an int, returns an int. It's called add5, and what it does is returns the input plus 5. So just a very extremely basic method that we want to write here. And the reason for that is that I want it to be very simple So we're not bogged down with the code itself while we're learning about unit testing, because unit testing is what we want to talk about. Every one of you can write this method. So let me just crank this out quick. Int add 5. So we have our return type. We have our input, which I'll name input because I'm not creative right now. And then return input plus 5. So that's our whole method. That's it. That's all it does. And now we can just look at this method and verify that it does what it's supposed to do. You can just look at it and see that it does add 5. Like there's no tricks here. There's nothing. It's just a simple method. But how would we know that? Especially if we weren't able to see the code. Oh, I can't really hide the code, can I? Because it's only one line. What if I just add a blank line? Yeah, there we go. So what if we can't even see the code? We want to be able to test this method, write tests for this method to make sure that it does do what it's supposed to do, regardless of how it does it. And I'll encourage you to write your test first before the code. A lot of students don't do that, and I'll try to not harp on it too much, encouraging that. But I do really want to encourage writing your test before the code when you're doing your assignments. I think it really helps when you're writing tricky code, especially. But how do we test this? And the first thing to do, I don't know, just look at the code and see if it's right. Is your first thing in testing. But I like to think of this as progressions. Like as you go throughout your coding career, you start to evolve the way that you test code. And of course today we want to get to unit testing, and we'll get to that. But just to kind of explain where we're at, I think the first way that students like to test their code is, well, you submit to Autolab. If Autolab says it's good, then it's good. And not do any actual testing at all. At the beginning of CSE115, that's perfectly fine to do. You're just getting your bearings and figuring out how this coding thing even works and what it is and everything. So just submitting to Autolab, that's what Autolab's for. It'll tell you if you're good or not. And then eventually, and hopefully by the end of 115, they got you to the point where you're doing the next progression. That's writing a main method and then printing to the screen the result of your method with some inputs. So hopefully you probably had, here's a very common office hour interaction in CSE1. I gotta learn how to talk and type at the same time. In CSE115 is you go to office hours and you sit down with the TA or the instructor and you say, is my code right? Or you say something like, I submitted to Autolab and Autolab says this isn't right, but it looks right to me. I think it's right. I think this code's right. Help me fix it, whatever. And through that interaction, the TA or instructor, what they'll do is walk you through, okay, how do you know this code is right? And you'll say something like, well, I looked at it and it looks right, so obviously it's right because I'm a god programmer. And then they'll see the error right away usually, but they're not just going to tell you what the error is. What they'll do is teach you how to write a main method and just call the function at that point in 115, call the thing that you're writing and just print whatever it returns to the screen. So if I call add 5 of 5, I expect this to print 10 to the screen. Add 5 of 7, I expect this to print 12 to the screen. Add 5 of 14, I expect this to print 19 to the screen. So if I run this program, I can see those outputs. And if I see the outputs that I'm expecting, now I'm feeling better about my code. And usually in office hours, this is where you would say, oh, I didn't get 10, 12, and 19. And then you use that as a clue to figure out where your bug is. And even if you haven't had that office hour interaction, I hope, oh my goodness, I hope that at least by the end of 115, you were doing this much as your form of testing. Just writing a main method, or in Python, it wouldn't even have to be a main method, but just calling the code that you're writing and just visually verifying with your eyes Does it do what I expect it to do? Is it returning what I expect it to return? So that's where I hope everyone's at, if not beyond that. Hopefully, I see a lot of you got task 1 done. A lot of you are already on unit testing. But this is where you should be by the end of 115, at least this far. If you're still not even calling your code and seeing what it does, one, that's impressive that you got through 115. But 2, you got to learn how to do some testing, because as the code gets more and more complicated throughout your career, throughout each course, and then your eventual actual career, you're not going to get away with that anymore. It's a bad habit that you're going to have to break eventually, is just writing code and not testing at all. Some people do that. There's buggy code that gets released. I'm not saying anyone does it exactly like that, but there's buggy code that gets released. We've seen code that's buggy. We've all used software that's buggy, that's glitchy, that lags, and is just crappy to work with and a terrible user experience. There are constantly games that are released with more and more bugs. My dog came to visit. He's right here. There are constantly games with more and more bugs being released, and it's not something we want to do. As developers, we want our code to be bug-free, perfect on all our test cases, all of our inputs. Everything should be working the way we expect it to be. And there are reasons to release buggy code that's not related to testing. Usually, the devs know about most or all of the bugs that are being released, but they have tight time schedules. Like, there's all kinds of other stuff that goes into it, and they just don't have time to fix all the bugs. That's a whole separate issue. But as a developer, you need to at least be testing, and to the best of your ability, if you got a bug, get rid of that thing, test it, and eradicate it. No, there's no unit testing on the midterm. Midterm, you can check the syllabus, but it's 4 traces. It's OOP and data structures. There won't be unit testing. So the traces there will start with a main method, just like all the traces in lecture as well. On the tasks, on all 8 tasks, you'll do unit testing though. Okay, so that's our first line of testing, or second if you count Autolab as the first line. Autolab, did I mention that? Autolab's not going to exist. In some courses, Autolab doesn't exist. And in the future, after you graduate, for sure, Autolab does not exist. You're not going to have any automated system that you can submit your code to and check if it's correct. That's a big part of what they hired you to do, is to produce accurate, correct code. They're not going to produce the tool. If they were to produce that tool for you, they would have just wrote the code themselves. It would have been a lot easier. Writing graders is way, way, way more work than doing the actual assignments. It's grading my solutions for assignments is usually where I finally get to take a breather and just do the easy part. It's the fun part at that point. So nobody's going to do harder work than the actual... Anyway, it's up to you to test your own code. So we start asking the question, how do we know our code is correct? Okay, main method's fine, but this is only going to get us so far. Okay, we're all just adding 5 and we're doing 3 test cases. That's fine. But this is going to get complex fast. And it's fine for 115, the types of methods you're writing, functions at that point that you're writing in 115. That's perfectly fine. You can get away with just printing the results to the screen and debugging your code that way. Once the programs get bigger, which is the theme of 116, how do we write large programs? Once our code gets bigger and more complex, where we have multiple files, possibly hundreds of files of code that are all interacting with each other and calling each other's methods and using each other's classes, things get really complicated really quickly. So when you have hundreds of files that are all interdependent on each other and you make a change in one of those files, how do you know that you didn't break anything in any of that code? You're going to have your main methods, right? You have all these main methods and all these classes. You run them all. You look at thousands of things that are printed to the screen and you check them all one at a time manually with your human eyeballs, right? No, I'm not doing that. Hopefully you don't want to do that either. We're not going to do that. What we want is to be able to automate that process and run all of our tests in a matter of milliseconds, have them just rip all at once with the press of a button, and let us know if there are any issues. And that's what we want to do today. So we want to write some tests. Adder. I'm adhering to the names over here too much. I can do adder test here. So adder test. What we want to create is a test class filled with tests, which will have test cases, and we want to be able to write all of our tests in an automated way, run them all in an automated way. So let's set that up. So first thing we're going to need another import statement, but this one isn't quite like the other ones. We're going to do org junit dot test. We're going to have our first import to an external library. Now what this means is that we're importing code that is not part of Java. So this isn't part of Java itself. We are, what we have to do is download the JUnit library from the internet and link it to our project so we have all the classes of the JUnit library available to our code. It is not pre-packaged with Java in the JDK like everything else we've used so far, array list, hash map, string, etc. All that stuff comes with Java. JUnit does not. So to do that, to get this import to work, we have to download the code. There's a lot of steps involved to make sure everything is working the way we expect it to. And this is where this pom.xml comes in. So when you clone the repo, both the examples repo and the homework repo, it comes with this pom.xml. And among some other things, the big reason we're using this is to define our dependencies. So this says, hey, we have this dependency of JUnit, and then a program called Maven, which runs over here. Maven will see this pom.xml, look at all the dependencies, download all those dependencies, and link them to your project for you. So Maven does all this in the background, and you only if something goes wrong, which rarely happens anymore, you don't even have to think about any of this. So all that happens in the background. I want to talk about it just to make sure you're aware that's happening. It's kind of a shame that it is so automated these days because you don't get to really learn about this and have to think about it very much. But JUnit is a dependency. We have one other dependency that we don't even use anymore, but we any other dependencies would go in here as well. Nope, that's not true. Never mind. So JUnit is the big one that we're going to use this semester, so it has to be installed. The reason I say all that, the reason I still talk about this even though it's automated for most of you, is if you do get an error on this import statement, that means something did go wrong with that process, and you have to do some Maven magic to be able to get this library installed. Usually when that happens, the most common cause of that is students who are not cloning the repo, which I forget, I did it in one lecture and not in the other, but I forget which one I did it in. If you're not cloning the repo directly, code example, yeah, this is the cloned repo, but if you're not cloning the repo from Git the way I recommend, the way it's laid out in the Piazza posts, and if I demoed it in this lecture, the way I demoed it in lecture, then, and you're copying code like one file at a time into a new project, that code isn't going to have that pom.xml, or maybe you did copy the pom.xml as well, but when you copy and paste that file, Maven sometimes doesn't see it. So in that case, you would have to right-click on the pom.xml, first grab it, right-click it, and then do add as Maven project. I don't have that option because it's already added as a Maven project. And then it should download your dependencies for you. So if you see an error here, that's going to be a Maven thing. I would strongly recommend just cloning the repo the way we show you in Piazza and in lecture. If you just clone the repo, there's a lot less that and other things, a lot less you have to think about and worry about. Okay, so next I want to do a different type of import statement. So then this goes along with the expectations in the syllabus. I expect you to want to learn about computer science. So I'm going to show you more of these little tips and tricks, some things that I would probably hold back on a 115, but in a 116, I'm going to show you some stuff that might confuse 115 students, but hey, you took 115 and said, yes, I want another semester of that. That sounds great. I assume that you're ready for more tips and tricks to make your life a little easier, even though it's more stuff you would think about. If you don't want to think about it, you don't have to do the tips and tricks when they come up. So I'm going to import static org junit test. You know what? Now's as good as time as any. I should mention this. So I'm using autocomplete here, where it gives me a list of, like, I hit dot and it gives me a list of all the things that I can call on that thing. This is, if you want to use that, that's fine, under the condition that if you do use this, like I can use it for assert right here. If you use it, it should be auto-completing what you would have typed anyway, and you have to fully understand what it's completing for you. If you don't fully understand what it was and you were relying on that, if you could not have written that code without the autocomplete, then that's not okay. That's not okay anymore. This is also very different than full line autocompletion. If you go into File, Settings, and search for full line, I don't even know if it exists in the Community Edition, which might be for the best. Yeah, it looks like it doesn't even exist, which is good. Fine with that. I expected it to at least be a setting, though. Oh, yeah, doesn't even exist. Good. But if you have full line autocompletion, so like the dot is just telling me the next thing, but if you're typing and it shows you a full line, like here's the rest of the line for you, that's not okay. That's AI assisted, and that is all day cheating. That is not okay. That's a good way to fail the class if you have that enabled and you're using that, where it's basically writing the code for you, where you can start a method and just hit enter, 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 and it can write the whole method for you sometimes. It's not always right, but it can write a whole method for you. That's not okay. That's different than what you'll see me using in lecture. What you see me using in lecture is the autocomplete. I do leave this enabled just because I don't always feel like typing assert true, which is what I'm going to do. I'll type it out this time, assert true. Like that's what I'm going to import, but I don't feel like typing the whole thing every time. I'll use the autocomplete for that, not full line autocompletion. Full line autocompletion, some students will go to office hours with it on, and like it's an obvious AI infraction at that point. So this is a static import. So instead of importing a whole class like we've done before, a static import is importing one static method of a class. So I have the assert class that's in the org.junit package, and I'm importing just the assert true method from that class, which is a static method. And if you control click or command click on Mac on anything in your code, you can actually go to the definition of it. So I can verify assert true is a static method in the assert class that's in the org.junit package. So just from the import statement, I can infer quite a bit about the code that I'm importing. I can even see, kind of thinking ahead a little, assert true takes a Boolean and asserts that that Boolean is true. If it's false, it will throw an assertion error and fail your test. Things that we'll talk about in a minute here. But that's what assert true is going to do for us. That's the method we'll actually use to write our test. So let's write a test. And this test class that we imported, so the static import was to import one specific method. So when I'm ready to call that method, I can just do assert true instead of assert true. Oh, Kobe, you're a menace. You turn off my surge protector. Good thing it's not the one this machine's running off of. Uh, so, and then test that we imported, this is a class. Oops. Oh, it's an interface, actually. It's an interface, some we haven't talked about yet. They're kind of like classes. We'll talk about the difference later when we talk about polymorphism. But this is an interface that's defining an annotation. This is something that we can use to annotate our methods. And we're going to annotate all of our test methods with the test annotation to tell JUnit that this is a test method and should be ran as a test. So I have public. Our test methods are public, void. They are not static. So this will be the first non-static method that we see, though the difference isn't going to matter to us yet, other than don't write the keyword static for your test classes, for your test methods. And so this is non-static, but not until Thursday. I mean, it's only 2 days away. We'll talk about the difference between static and non-static. But for now, JUnit needs non-static methods. And then we're going to name our method, which will be the name of our test. So I'll call it test add 5. Seems like a fine name. And then test methods do not take any parameters. So this is our first test. And all that talk about static, if I do put static, if you just make everything public static, IntelliJ is just going to tell you, hey, that's annotated with that test, it has to be non-static. So it's not really something you have to memorize. It's not a mistake you can really make. If you have static here, it's going to tell you, you try to run this, it'll tell you. Like, there's no way to miss this. Invalid test. Test add 5 should not be static. You can't get much clearer of a message than that. I did, side story, I'll keep this brief, but I was looking at a lot of C code the last few days, and C error messages are not clear. They are not like this. In Java, the messages are just so straightforward. It's such a relief to be back in the world of Java right now after digging through a bunch of C. I was digging through a library that was not mine and had hundreds of thousands of lines of code trying to figure out what was going on with it, and those error messages are not really helpful. Okay, so I mean, they're helpful but not as helpful as Java's, and even with C they've gotten a lot better over the years. Okay, so this is our first test, and the name of the method is the name of the test, which means when we run this, now that it doesn't break, when we run this, we're going to see the names of the tests over in our feedback after it's ran. So the name of the test, it's advised, I recommend that you use meaningful names for these because it's going to be easier to read your outputs. Some of you will do test 1, test 2, test 3, test 4, test 5, and then in the feedback it says test 3 is failing, and then you have a little bit of extra brain power to put into it, like, okay, wait, what one was test 3? And then you go to test 3. Oh yeah, that one was test 3, the one that was doing this. Just name your tests after what it's doing, and then it's a lot easier to read the feedback. And also when you submit to Autolab is going to use your test names when it's relevant to give you some feedback about your individual tests. So if you use meaningful test names, it's a lot easier to read your Autolab output as well, because it'll just say, oh yeah, test add 5 broke. Oh, that's the test where I was testing the add 5 method. It's a lot more straightforward. Okay, but now that we have our tests set up, now we're ready to actually write some test cases. And this is where we're going to write the code that we had in our main method, but we're going to write it as a JUnit test. And this is where we're going to use that assert true method that we imported. So assert true, and I want to assert, that 10 equals add 5. I'm going to do this wrong the first time, actually. Add 5 of 5. And I'm going to get an error. I can't just call add 5 like I did assert true because I did not statically import add 5. And this is the same thing that's going to be true in your assignment, is you need to call static methods through the class where it lives. So I need to do adder dot add 5. Oh, I'm on assert true still. I'm going to assert that 10 equals whatever this method returned. So if this method returns 10, I have 10 equals 10. That's going to resolve to true. And what assert true does is takes a Boolean expression and asserts that it's true. It's going to check if it's true. If that Boolean expression resolves to true, assert true says, good. That's what we wanted. Cool. And then it just moves on to the next line of code. If assert true gets a value of false, then the test will fail and it'll say, hey, your code is wrong here. So let's get a few more test cases here before we see that. So input of 7, input of 14 I think I used. So 12 and 19. So here's my first test. I'm going to assert that all these are true. On an input of 5, my method returned 10. On an input of 7, my method returned 12. An input of 14, my method returned 19. And this is all fully automated, so at the click of a button, I can run this test. Why do we do adder before the method call? So we're calling the add5 method from the adder class. So I have this class adder, which has an add5 method that I'm calling. So I do adder.add5, which is the same as if I didn't do a static import here. Then the assert true method, I'm actually calling through the assert class. So I would have to do assert.assert true on every one of these method calls. It's the same thing that I'm doing with the adder.add5, is I'm calling a static method through its class, so I have to specify the class. Same thing with your problem set. You have to do problem set.average, problem set.sum of digits, problem set.best key. You have to call those methods through the problem set class because that's how we call static methods, unless we do static imports. If we're statically importing the method, then we can just call the method directly. There's also one other thing you're going to need on your homework. You're going to have to do import, where are we? Week 3 dot lecture dot adder. So you're going to have to import the class itself too. So you're going to have to import your problem set class to be able to call these methods. We don't have to do that here because these two classes live in the same package. Any classes that are in the same package do not have to import each other. They're automatically imported. All classes in the same package as your class are automatically imported. But if we wanted to do a static import, and you can do a static import, it can save you some typing on the homework. If you statically import all of your methods, if we statically import add5, now we don't have to do adder.add5 anymore. We just do add5 because we statically imported the add5 method. So if you want to cut down your typing, go for it. For my preference, I like to not do that. If it's my code that I'm calling, I like the reminder of what class I'm working with each time. So I know that this method lives in the adder class. But when it's the asserts from JUnit, if I see an assert, I know it's from JUnit. So I don't want it to type assert dot every single time because I know it's from the assert class of the JUnit library. So that in that case, I'll statically import. Okay. Running this thing. Okay, so we have our test cases and we want to run it, and we see some go buttons, and I was clicking this one earlier, but I want to go through these ones because you'll see a whole bunch of these, and it's important to make sure we're clicking the right one. In this case, they all do the same thing, but they won't by the end of the lecture. No, maybe I should just wait till then, but I want to run this thing, so let's talk about it now. So this button is going next to the method, is just going to run this test method. And this one, which usually we don't want to do, I'll do it a little bit today, but usually we don't want to do that. But this one next to the class is going to run all of the test methods in that class. That's the one we're usually interested in. We want to run them all. But it's really easy to click the wrong button. I've clicked the wrong button plenty of times in my career until I finally developed the habit of right-clicking on the class itself and then going to the run button here. That one is always going to run the whole class, and I won't have to worry about anything else. I run the whole class and everything's, I'm not going to miss my test case. I'm not going to accidentally only run one of my test methods. All right. And this is what it looks like when your test passes. We got green checks, but I always like to watch my tests fail, which might sound weird the first time you hear it, but I like to watch my tests fail. A lot of developers do. It's not just me. So what I'll do is, if my test has always passed, I haven't seen it fail yet, is I'll go and intentionally break my code. Oh, and then this go button up here will run the last thing that you ran. The last thing I ran was the adder test, so now I'm going to use this guy up here. Be careful with this one, though. Sometimes it'll run not what you want. And this is what it looks like when your test fails. Test add 5 failed. It'll give me a stack trace, which is all of the stack frames that were on the stack. Test add 5 was on the stack on line 11 when the crash happened. It was an assertion error, meaning one of my assert trues got the value false, and it was the first one. So once an assert fails, that's it. It's game over. So once this assert failed, the assertion error was thrown and nothing else happens, the whole program shuts down, or that test method shuts down and doesn't move on any further. So these next 2 test cases were never executed because the first one failed. This is where we demand perfection. We have to pass every test case. We need 0 bugs. That's how we want to write code. We can't have any bugs in our code. So the first test case just failed. Now I'm going to fix that, run my tests again, and they do pass this time. So this go button is going to run the last thing that you ran. You can change that behavior. You can change it to current file. I like it running the last thing, which is the default. But you can change it to current file to always just run whatever file you're currently editing. But often in case that's not what you want. When your programs get larger, often you'll be running code that's not in the file that you're currently editing. So then you always have to click back to the file. And this is a good case. If you write your test first, like I recommend, you'll be in your test file just writing test cases, and then you're going to go to your code, write some code, and then run your tests. So you're running a file that's not the file that you're currently editing. That's very, very common. Once your programs are multi-file programs, you're going to have that a lot. Okay, so we have our tests. We have our test inputs. We have them set up in a test class. Everything seems fine with this. But now we can revisit that question. We can kind of rephrase that question from the beginning of lecture is, how do we know our code is correct? How do we know our code's fine? So we've automated our tests so we can check with the click of a button and a bunch of green check marks that it passed all these test cases, and I don't have to get my human eyeballs involved anymore. I don't have to look at what was printed to the screen. I don't have to do any of that. But is this enough testing? Is now what our question becomes. Is this enough testing that you're confident that if this test passes, the code must be correct? Even if you can't see the code of the add5 method, that if it passes these test cases, you're saying, yep, that code is correct. I bet my life on it because it passed my tests. Now, that's a tricky question to answer in general. In this specific case, hopefully you're all screaming or at least thinking, no, that's not enough testing. Like, you have 3 test cases. They're all small positive integers. This isn't enough testing. If any of you think this is enough testing, I bet you're going to write a lot of buggy code. Or please break that habit before you graduate so you don't write buggy code that I'm going to have to use in the future. Okay, so I don't think this is enough testing. And we can go to our code. One way to do this is to go to our code and break it in a way that passes our test. So if we do something like this, if I take the absolute value of the input and add 5 to it, this implementation is now wrong. This isn't correct code. I'm going to run my test, and it passes this test. So we have incorrect code that's passing on our tests. This is a bad situation to be in. It means our tests are broken, or not broken in this case. It means our tests are not thorough enough. We don't have enough testing here. So we need to go to our next evolution of testing. And I'm going to create a new test method for this. So I'm going to pull out my annotation again and write a new method. And this is something we can do and something that it's recommended to do to organize your stuff. Admittedly, it's not too helpful on task one. On task one, I would expect you to have at least three methods, but three suffices, one for each of the methods that you're testing. Don't put all your tests in one method that tests all three. That gets cluttered and clunky, but we can separate our test cases when it's meaningful into other methods. So let's do test add 5 negative inputs. So let's get rid of the negative numbers here. And I'm going to copy and paste so I don't have to type so much. And start generating some negative input test cases. So let's do negative 10, should be 5. Negative 7, sure, should be 2. Ooh, those are broken test cases. Negative 5 and negative 2. Negative 100 should be negative 95. And I want at least one test case that crosses the threshold from negative to positive. So let's do negative 3 equals positive 2. So now we have negative test cases, which I would call our uncommon test cases. We want to think of the common test cases. These are test cases that anyone off the street is going to think of. Hey, I have a method that adds 5. Or, what input would you give it? I don't know. Small positive integer values. That's what the first things that are going to come to mind to pretty much anyone. Then a little trickier, what I would call the uncommon cases would be our negative inputs here. This is like when you study for the SATs, they kind of really drive into your head that, hey, negative numbers exist. You better be thinking of them all the time. That's very applicable in computer science. We need to think about what happens when we get a negative input. Is our code going to handle that properly? Right now, our code definitely does not when I added that absolute value. So we're going to pass the add 5 tests, but not the add 5 with negative inputs. We're going to fail on these ones, and we should fail on the very first one, and the rest of them aren't executed. And this is what I mean by meaningful names on your tests. It's very easy to read this output and figure out what happened. I'm doing well on the positives, but not the negatives, so I can start narrowing down where the bug can be. Because if a test case fails, well, the purpose of any test case is to expose a potential bug, and if I have meaningful names on these and meaningful separation of my test cases, it narrows it down, gives me a lot more information for my starting point to be able to figure out where that bug is. Because I know I'm doing good on positive values, but negative values I'm not. So I'm looking for some way that my code is failing only on negative values. And of course, I can see it right here. Oh, I'm taking the absolute value. That's ridiculous. And then we can fix our code. It's not, most of the time, it's not going to be that easy to find your bugs, of course. And now we pass the negative inputs and the positive inputs. So we're feeling good. Might as well label this while we're here. Okay. And this is the level of testing that you should have. Is the bar should be, if you can't, and I said this before, but this is where the bar should be, is even if you can't see the code, you are confident that it's correct. You're confident that that code must be correct if it passes all of your test cases. Now, in most situations, you're going to be testing your own code, and you do have access to the code, and developers get a lot of bad habits where they'll write their code, and then they'll write test cases very specifically for their implementation of the method. And the test cases are very, very narrow in focus. One way to avoid this is to write your tests first. I will always recommend this, but but it's a hard battle to get students to actually do it. But I do recommend writing your tests first when you're doing the test, especially when the methods are tough. Maybe for the average method, it's like whatever. It's the average method. You're you're probably not going to make any mistakes writing that code. You might, but you can tackle the code first. Whatever. But when the methods get more complex and you're not quite sure how to approach the problem to begin with, writing the tests first can be extremely helpful. You write the tests first, that forces you to think about what the behavior of the methods should be, because you have to write test cases for them. So you have to fully understand what they should do. And then when you go to write the tests, you can run the tests as you're writing the code. You can run the tests to see if your code's right. So I have all these test cases. Then I write my code, and I'm looking at my code. I'm like, man, that's some beautiful code. I wonder if it's actually right. Well, I don't have to wonder. I'm going to run my go button. My tests pass. Great. If my tests fail, then I can start the debug process. I can look at which test case failed and then start using that to go on my debugging journey and figure out where the bug is and then eradicate it. Without the test cases, if I just have the code and no test cases, it's going to be a lot harder to find the bugs in my code until I eventually write the tests, and then I can find my bugs. But it's going to be hard to find those bugs first. So I recommend writing the tests first. And I say this is a losing battle, but here's the potential lie that I tell myself is, I hope this isn't a lie, but the students that I see in office hours, like anybody coming to me with their code and saying, why doesn't this work? The vast majority of the time, they wrote their code first and then their test cases last. It's kind of the natural way to approach problems. It's hard to do it in reverse for the first time. Most of the ones coming to me with issues don't do that. So it feels like nobody writes their tests first, but I like to believe that anybody who writes their tests first, that there are a lot of you out there who do that, but anyone who writes their tests first doesn't need office hours. You don't need me at that point, because it's so much easier to write your code once you already have well thought out tests, that you're never going to be in office hours for me to see that you wrote your test first. So I never get the satisfaction of seeing what we call test-driven development. I never get to see it because you just don't need me in the TAs, which is eventually where we need to get you. We need you to not be dependent on us, because we're not going to be there throughout your whole careers. So testing is one of the first steps to that progression of being completely independent developer who can write bug-free, correct code. And when a test case fails, actually I'll just set it up first. But when a test case fails, we're going to use my next big tip, the debugger. Students who write their tests first, then their code, and use the debugger when their tests fail, I never get to see those students because they just have beautiful code that they wrote in a minimal amount of time. And the students who don't do that, those are the ones who are pulling all-nighters and stressed out at deadlines, coming to office hours and panicking, trying to figure out why their code doesn't work. I think that's one of the big differences. So I do urge you, again, this course has a very high failure rate, and I do not like that. It doesn't sit well with me. And one of the big things that we can do to lower that is write tests first and use the debugger. I think I haven't seen a student who did both of those things and also failed the class. That doesn't happen. So there's your keys to success. Okay, so now I keep saying write your tests as though you can't see the code, but you can see your code like you're writing it. And why is that the standard then? Why would I say write it as though you can't see the code? It's because sometimes you can't see the code because you can't see what that method will be like in the future. So here's a common situation. You write this method. Okay, I got the test, add 5, writing this method, input plus 5, done. And then later on down the road, you have some meetings with project managers and stuff, and they're like, our code isn't running fast enough. We need to optimize everything. Everything needs to be optimized. Everything needs to run faster. And somebody's going to come along and look at this method and rewrite it because they want to be part of the optimization thing. Some hotshot intern who's way too smart for their own good is going to overthink a simple add 5, which shouldn't even be a method to begin with, is going to overthink this method and try to get too cute with it. So what they're going to do is something like this. They're going to say if input is greater than 0, this is going to be the same person who did the math.absolute value dumb thing. So they're going to say, well, math.absolute value, you didn't like that because it didn't work on negative numbers. Okay, so that's fine. So if it's positive, I still get to do that. I can still do math.absolute value. Yeah, this is good. This is great. Math.absolute value input plus 5. This is the code I had before, but now it's going to pass your negative inputs. Yeah, that's great. Okay, but I do got to do something else for the negative inputs. So let's do an else if. Let's see. Input is less than 0. Now we have a negative input. That's going to return. Okay, now how do I actually fix the negative? I love my math.absolute value, and that's going to be super efficient. I heard this is a very, very fast operation. So let's do math.input still. We've got to add 5 eventually because that's what the method does. But let's just take the negation of the absolute value. Yeah, that looks good. We're going to take the negation of the absolute value. Oops. And this. And then they're going to get to this point here. Can you show us how to test with arrayless inputs? I mean, one step at a time, Negro. Let's we will get to that. Let me. After this example, I'll whip up a quick one for you. But let's learn what unit testing is first and finish this one up. Don't let me forget, though. Yell at me if I don't get back to it. So then they get to this point, and they're like, okay, I handled positives, I handled negatives, but Java's yelling at me. It's saying missing return statement. I have 2 return statements, so I don't know. I'll give you a third one, I guess, but what do I return? I don't know, just the input, I guess. I don't know what to. I already handled everything, so let's just return the input there. Okay, optimize. They go into the meeting. They're like, I optimized the add 5 method. So now when you wrote these tests, you did know what the code was, but you didn't know that somebody was going to come along in the future and rewrite that method. And this does happen. This is an actual scenario that happens all the time. You have code, it works, but it needs to be optimized. So somebody's going to way overcomplicate it. Hopefully they're actually optimizing. Like, this is way slower than what we started with. But hopefully they're actually optimizing. And sometimes the code can get up to like 10 times longer, but be much, much faster. And that's a topic for another course, but that does happen. That is a thing. And then you want your tests, which we're testing very simple code, to still verify that the complex code is correct. So we run our tests, we run our adder tests. Let's make sure our code is still correct. If I did this right, okay, passes. But we should know, you should all catch that, I hope, that the code is not correct. It's not the right code. So a few things going on here. One, the return statement, when it said missing a return statement, we already have 2. The reason for that is that we need a return statement, recall from last Thursday, that we need a return statement for every path through our code. We have an if, we have an else if. We don't have any else in this code. So if neither of these conditions are true, then it's going to fall through. It's not going to hit any of these blocks. And it's going to fall through here. And in that path through the code, there is no return statement. So we could either add an else. I'm going to add an else. I think that's the way I want to handle it. So we can add an else and then return input. We can do it here. But we do need a return statement through every path of the code. So either an else or just after the conditional, returning something. That makes sure we always return something. But we're missing something here. Actually, I don't want to go to the code yet. I want to go to my tests and make sure our tests are actually testing everything that we want it to test. So this is the last type of input that I'll talk about here, is what we call our edge cases. So add 5 edge cases. I want to think about the situations that can really trick the code. And when you're writing tests, that should be your attitude. You're trying to break your code. You want to try to break it. And you want to challenge it. When you test your code, you really want to test your code and make sure it is always correct. And sometimes there's very specific inputs that your code has to handle very specifically. I mean, the code here in this example doesn't have to do anything different, but it will in other examples, in the next one. So for this one, and most of the time, these are your inputs of, say, 0 for ints. Anything that's going to result in 0, like -5 here, these would be my 2 edge cases for this method. If it's a string, the empty string. If it's an array, an empty array or array list. If it's a hash map, an empty hash map. Those really tricky, not really tricky, but those special situations. Like for the average method, what does it do when you give it an empty array list? Well, it has to do something different, which is going to be... Oh, is that what you mean by testing with array list inputs? Oh, you're talking just inputs for like the average method. I better cover that. So these are the inputs that have trickier outcomes. So these are my edge cases here. Let's rerun our tests. And of course, that new code, that fancy code, does fail the edge cases. It fails the first one. On an input of 0, we get the output of 0 instead of 5. Actually, now is a good time as any to talk about this. Is any assert can take an optional first argument that's going to be a string, and this string is printed to the screen when the test fails. So and then it gives us some extra information about the test. So on input 0 returned, let's grab this, we'll call the method twice in this line. It's a little cumbersome, but just so we can see what happened here, on input 0 returned 0. So we returned 0, and this is where I'll get the first debugger in here. I like to do a debugger example whenever I can. So here's our first one. I'll just give you a brief taste of it today. Is I'm going to set a breakpoint by clicking on the line number and then run my code again, but instead of using the run button, I'm going to use the debug button, which is right next to, no matter where you're running from, debug is always right next to run. So I'm going to run this in the debugger. What this does is runs my code until it hits a breakpoint, and once it hits a breakpoint, it's going to show you everything that's happening in memory at that point in time, and lets you step through your code one step at a time to see what's going on in your code. So we can just run through the code and see exactly where it goes wrong. If you use test-driven development and the debugger, hell, if you just use the debugger, if I'm being honest, if you use the debugger, you're never going to have issues. Learn how to use the tool. The tool is not the easiest to use, so it will take some time to learn. And if that's your question, office hour, you come to office hours and say, man, I just don't understand this debugger. Can you help me learn how to use the debugger? Oh, man, I'd be thrilled. Most questions in office hours are, the code, Autolab's not giving me points, fix it. If you have a nice, thoughtful question, oh, it's so nice. That said, if you have the question of, Autolab's not giving me points and I don't know what to do, that's still a valid question, don't get me wrong. It's just that that's the most common question. At this point, I just like anything that shakes things up, as long as it's not too negative. So we can step through our code. And one thing you may have noticed about my tests here is that there's no main method. I made a big deal all last week. Like, every Java program starts with a main method call. Every trace that I do, I'm like, every Java program since the dawn of time starts with a main method stack frame, a main method call. There ain't no main method here, but I'm still running it. So what's going on here? So there is a main method. It's just not in our code. And we're not actually running our code. When we run a test, we're not actually running our code, not directly anyway. What's happening and what we can verify in the debugger is that we do have our two stack frames here. This is showing our stack frames. So we have the test add5 edge cases stack frame, which called add5. So there's an add5 stack frame with the input equal to 0. So we have our stack frames showing us the same information we have on the in the memory diagrams, in the traces, but we can also see a lot of other stack frames. There's more than just our code on the stack here. There's a lot of overhead with the JUnit library. So what IntelliJ does is runs its own main method. When we think we're just running a test case, what we're actually doing is telling IntelliJ to run our JUnit testing. And IntelliJ is smart enough to know what JUnit is and how to set it up and everything. So there is a main method. Here's our main stack frame right here, the bottom of the stack. And then it called a whole bunch of other methods until eventually got to JUnit, and it called the JUnit run method in JUnit core, which did a whole bunch of other overhead and everything. And eventually there's we can't even see where we are in that one. Eventually it called a method which called our method. It created a class of type adder test and then called our non-static methods. Created an object of type adder test and then called our non-static methods through that object. So all of that did happen. It's just all behind the scenes. So trust me, there is a main method. We just don't have to think about it. Every Java program starts with a main method. That's still true. Okay, so we get to this code. Input greater than 0, and we can kind of do it just like we're doing a trace. There's a reason we do those traces so often, because it's going to help you go through your code and find your bugs in the real world. It translates over pretty well. So input greater than 0, input is 0, so I expect this to return false. When I run the debugger, I like to predict what the line is going to do, and then step through and make sure it did actually do that. It did what I wanted. Input 0 less than 0 should be false. It's telling me it's false right there anyway. This should be false, so I'm going to go to my else, and my else just returns input, this else that I just added because I thought I had everything covered. Well, it is actually being hit on an input of 0. It's not positive, it's not negative. It's going to return input. So I found my bug right here. On 0, I'm going to return 0. So let's add a good old +5 right here. Hell, we could even just return 5 if we're being cute about it. Just return 5. And now we should be good. So once I find my bug, I'll shut down the debugger and then run my tests again to see if I'm done. Because if I get green check marks here, I'm feeling good. I got green check marks, I'm passing all the tests. And just verifying this method's simple enough, I can just verify that this is doing what it's supposed to be doing. It's overly complex. It's a dumb way to implement this method. But it does pass our tests. So especially if you can't fully wrap, well, it's not that complicated. You should all be able to wrap your heads around this. But if you don't fully understand what's going on here, even in that situation, we have an implementation of add5 that passes all of these tests, all these test cases. If you have any implementation of add5 that passes all of these test cases, is that enough testing? Are you confident that that implementation is actually correct? Or would you want to add more testing? If the answer is, I'm not confident that it's correct, it's a good sign you want to add more tests. Maybe we want some very large positive values here. Is one thing I would definitely want to add. Some very large magnitude negative values I would want to add. There's more testing we can do here, and that's where it becomes a tougher question. It's up to each developer, up to each of you to decide what is enough testing. Now in 116, Autolab sets the bar, admittedly pretty low. It'll accept some pretty crappy testing and still let you be done with the assignment, just because I don't want to be too overbearing about it. But after 116, some of you will disagree with that. Some will be like, well, I have 2 test cases and Autolab's not saying I'm done. What the hell, man? I hear that every semester and it's exhausting. But there is a pretty low bar. And then after 116, or even after you cross that bar during 116, it's up to you to decide how much testing should I have to be sure that I'm not releasing buggy code. And you can never be completely sure. You can never get to 100%. But unless your method takes a Boolean, I guess. You can write your 2 test cases and you got full coverage. But it's up to you to decide. Do I need more testing with this? And with this specific example, you're like, it's just adding 5. I don't need any testing. But once the methods get more complicated, how much testing do you need? How much testing do you want? Is a big question. And it never hurts to just add more test cases. If you're not sure, just add more. Add more. It's never going to hurt. And variety goes much further than just strictly more test cases. I've seen students with 20, 30, 40 test cases, and like you keep saying more tests. Autolab feedback says more tests. Everybody says more tests, so I'm just going to add more tests, but I'm still failing in Autolab. Autolab still doesn't like my tests, and it keeps just saying adding more tests. But then when I look at their tests, all of their tests are of this flavor. Like for this example, it would be positive integers. They'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, up, and then maybe a few different ones like 100, 120. But they'll have like 40 test cases that are all just positive integers. And it's like, yeah, you have a lot of test cases, but it's all about variety when you're adding more test cases. Having another positive integer, if I add a test case for 11, that's not going to expose any more bugs. And again, that's the job of test cases, is to expose potential bugs. If the bugs exist, the test cases should expose that and let you know, hey, there's something wrong here. You should look at this to fix your bug so you don't release a bug to your end users. Test cases need to expose that. Adding 11 here isn't going to do much work. Yeah, maybe there's some really obscure implementation of add 5 that fails specifically on 11 but passes on 7 and 14. It'd be a really wacky implementation, but it's not. I'm not going to get much mileage out of that. But if I don't have any negatives and I add my first negative test case, I'm getting a lot of mileage out of that one. That one's a really good one to add because it's different from the test cases that I already have. So getting that variety more than volume. And hell, if I wrote this as an Autolab, if it was an Autolab graded method that you were writing, this add 5, you could get away with 3 test cases. I would make sure you have 1 positive, 1 negative, and 0. If you have those 3 test cases, I would say you're good on testing. That doesn't mean it's a good set of tests. I would definitely in the real world want more than that, but that's what I would do for an auto grader. I would make sure you have those 3 test cases. Make sure you have 1 in each category. So you could get away with 3 test cases. And arguably, even in practice, some people might argue, yeah, those 3 test cases, you're good. I would tend to disagree, but there is a debate to be had there. It's not an automatic. It's not an automatic thing. Okay, and I already showed you hint text, but one more thing I want to show that can help your tests, and it's the reason why all these assert trues are giving me warnings, is that there's something better we can do. Shouldn't say better, but something different we can do is assert equals. So we can, instead of asserting a Boolean expression, we can do assert equals to check if 2 values are equal to each other. I'm getting errors because I didn't import this, so I can do import static org.junit.assert equals. I can do that, but if I'm going to use a bunch of different asserts, or even if I'm not gonna, just in case, you can use a wildcard here and do assert star, and this is going to import every assert that you have available to you, of which there are quite a few. Assert true with a hint string, assert true without a hint string, assert false, fail, which is sometimes useful. Usually you can rewrite fails as an assert, but sometimes fail is useful, or just straight up fails the test. Obviously in a conditional, if some conditional fail, but at that, yeah, there's situations where it's helpful, but not. It's kind of rare because usually you would just say assert true the conditional, but sometimes assert equals, which we're about to talk about. Assert equals regarding null. Is equals. How is that different than assert equals? Expected dot equals. Oh, just straight up calls equals. Assert equals. Okay, that just directly goes to equals instead of mucking around. Assert not equals, fail equals. There's a few that are useful later in the semester. I want to at least get to those ones. Assert array equals. Oh, we don't use arrays in 116. Not array lists, but arrays. Oh, we'll get there eventually. There it is. And assert null and assert not null. That one's not assert not null. Assert not null. With and without hint strings. Every assert has either a hint string option or a no hint string option. And these can be useful when we start talking about linked lists next week. Assert null and assert not null. But anyway, you have a lot of asserts. If I do import star, this is the wildcard that imports every static method from the class. So I can just use them all now. And this is going, assert equals takes two values, or potentially, we could have a string. We can also have with or without hint text. And it takes the value you're expecting and then the value that you're testing. And if the two are equal, it's going to pass. If the two are not equal, it's going to fail. So if we go and break our code, that was a positive value, so let's break the positive. So assert equals is a way to clean up your tests. Instead of continually writing assert true for all these, assert equals can clean up your tests. It's just a little easier to read assert equals sometimes. Maybe that's debatable too. But a bigger advantage is that the output it gives you is a little more meaningful. Where assert true is just going to say, hey, the assertion failed. You asserted true and it was actually false. Assert equals will give you more information. It'll take the two values and say, this is what you told me you were expecting, and this is what was actually returned, without having to use a hint string to be able to tell us what was actually returned. The hint string is sometimes useful to give the input. Input was 5. Assert equals is not going to tell you what the input was. It has no way of knowing what the input was. So in my hint string, sometimes I'll put the input, and then assert equals will tell me the rest of my information. I'll have all information. My input, my expected output, and my actual output. Those are the three things that I want to have when I'm asserting, when a test case fails. That's what I want to know. If I'm testing an input-output behavior method. There's one more thing. Yeah, array lists. Okay. All right, I'm getting to your question. Let's do this. This kind of quick. Times. Not too tight, but we do have to. We can't dawdle too long. So I have an array list of. Do I have anything handy? What do we do? Oh, none of those took array lists. Do we not have an example that took an array list yet until later? Well, no, we have this method right here. Right? Yeah. Yeah, we wrote this method last time. We did a trace of it and everything. Yeah, we did have a method. I was gonna say that's a big oversight since I asked you to do it on the homework. All right, so let's test this one. So in the array list example, so let's import week 1. Yeah, week 1 dot lecture dot array list example. Yeah. Autocomplete's failing me. What am I missing? Import week 1 because it's week 2. Huh? Week 2 array list example. And then we want to test for that. So we're going to call array list. This was integer numbers equals new array list arrays dot as list, which It's an unfortunate one to spell incorrectly because then I'm not going to get my auto import either. There we go. Arrays.asList 148. And then we want to do array list example dot sum of numbers int answer. I'm always going to use the primitive unless I have to use the other kind. So when you have an array list as a parameter, there's nothing special. This is why I don't have a lecture example prepared, just pre-canned, because there's nothing extra special about testing with an array list as a parameter. You set up your array list the same way we would do before. If you don't want to use arrays.asList, you can create the new array and then do numbers.add, numbers.add, numbers.add. You can do that too. Once you have your numbers set up, call your method with that input, grab whatever the output is, but the input, it's still calling a method the same way we did last week. And then the answer is an int. So I made sure on task 1 that what's returned is not a data structure, because that's a whole new level of, we have to do other stuff that we haven't learned yet. It's not tricky. I mean, with what you have, you can do it, but for the first one, it's just a bit much. And then at that point, it's assert true. Assert true. I can use assert equals here. I expect the sum to be 13. Answer. And there's my test case. I'll run just this method. And we pass. I like to see my stuff fail. So let's break our code, run it again, make sure it is actually testing what we expect to be testing. We got 14 instead of 13 that time, so it looks good. Run it again to make sure we didn't break our code, and good. Looking good. So that's how we would do it. Same with hash map for best key. Create your hash map just like you always would. Call your method with that hash map as an input. Get your answer, and then assert. At that point, you're asserting a string, which is the next thing we'll talk about. You're asserting that a string is the value that you expect. Testing in Autolab was the one thing. It was the last thing I'm trying to think of the slides. It was the last thing I want to talk about. Is you have these test cases, and then when you submit to Autolab, you're going to get some feedback. Might as well just show you. Why wouldn't I just show you? You're going to get feedback that looks like this. So first, I'm going to check your testing utility. We're not doing that on task 1, but that will be, I guess I still have the feedback in there. There's no testing utility, not required. So you auto pass that one. And then for all tasks, you will get the rest of the steps. There's a few that don't have testing utilities. Task 8 notably doesn't. And then I'm going to test your test. So correctness of your test. You're going to see this is the output. Something like this. And these test names, these are what you named your test. So all those test methods that you have, whatever you have for your test methods, they're going to show up here, and it's going to tell you if there are any issues with this. So this is running your tests and a correct solution in Autolab. So I have a known correct solution that will always return the correct answer. It's a passing, fully complete implementation of all these methods. And I'm running your tests against that correct solution. So your tests better pass everything in that correct solution. Your tests better say, yep, this is a correct solution. If it doesn't, there's an error in your tests themselves. So either one, you have something like test average where what you're asserting isn't actually the average of all the inputs. So in a case like that, you got to go to your tests, just find the mathematical error and fix it. And then more commonly or more trickily is this guy. I have a well-named test case for it right here. Is for test key, this is specifically asking you to, specifically, I guess, teaching you, giving you practice with the possibility of a method that has multiple correct answers, multiple correct return values. This is the cat dog example from the handout. What happens when there are multiple correct values? One of the common mistakes here is, well, my code returns cat, so I'm going to assert equals cat is returned. And then you submit to Autolab, and my correct solution correctly returns dog, which is a correct solution, but your test fails my code because it was expecting cat instead of dog. So your code passes your test, fine, but your test is wrong because it's rejecting a correct solution. So that's what this first section is telling you, is how are your tests just flat out broken or not? If they're failing a correct solution, they're broken tests and you got to fix them. And the answer to that, with multiple best key, multiple answers, that's a situation where we can't use, like, you might get used to using assert equals. We can't use assert equals on that one, though. Assert equals is made for the specific situation of asserting if two values are equal to each other. That's what it does, and it does it really well. But when there are multiple correct answers, you're not asserting that something's equal to a specific value. You're checking if it equals one of two different values. So in situations like that, like the assert true, assert null, assert not null, all those other ones, they can be handy. They can clean up your tests. They can give you specific feedback and everything. They're nice. But assert true is your sledgehammer. Assert true is always going to be able to do what you want it to do. If the only assert you ever use is assert true, you'll never get in a situation where you're like, oh man, I don't know how to assert this. If the only assert you use is assert equals, you're going to get jammed up more often than not, because assert equals doesn't always do what you need it to do. Assert true is always going to do it. Assert true, any Boolean expression that you can write, you can assert. You're not limited at all by any structure. So assert true is the return value cat, or is the return value dog. You can write that. You know how to write that. That's easy day. Easy day. The only thing, I don't remember if I mentioned this in lecture, but an or operator in Java is double pipes. So shift and then the key above enter. Double pipe is your logical or, instead of the literal word or, as it was in Python. Okay. With that, moving on. I think I want to talk about interpretation and compilation right now. I think now's the time. I don't do it now in lecture, but I feel like doing it right now. So let's talk about interpretation versus compilation. When you have code that's interpreted, there's a big difference between these. What would and be? Double ampersand. So shift 7. That would be your logical and. I guess we can demo that a little bit more. So true and true is going to return true. False. It's and, just like you would expect. And then if we switch it to or, this is going to be true. True or false is true. And then false or false. And obviously you won't have Boolean literals. You're going to have Boolean expressions. 5 equals 7, or, you're going to write your whole Boolean expression. But or, double pipe, double ampersand. I'm new to coding and want to be AI/ML specialist. How should I start? Good question. Taking a CS1 course, I guess. This is a second course in computer science. If you can understand what I'm explaining here, then this might be a decent place to start. But if you're not ready for this stuff, if you're doing the dead basics, that's a little tougher. I want to answer you without just saying Google it, but there's so many good resources out there. I like W3 Schools. I don't know how good that would be for a very first intro. And there are free courses out there like CS50, especially if you want to get to AI/ML. CS50 might get you there quicker. It's going to be a fairly quick pace, pretty intense, But you can also go at your own pace because it's just online. That might be a decent place to start too. Or always just enrolling at a university. I might be a little biased on that one, but there's a lot of self-learning tools out there too. All right, in AIML, there's a lot going on in that right now. It's a hot market. If you can do that well, uh, you're in high demand. That said, the market shifts so quickly these days that who knows what it's going to be in a few years. So, but right now, AI and machine learning it's hot. You can tell it's in the news every day right now. You know how hot it is right now. Okay, so interpretation versus compilation. So interpretation, if your code is interpreted, your code is executed one line at a time. So when you run your program, it'll execute line 1, or rather line 1, line 2, line 3, line 4, and just execute one line at a time. And a behavior of an interpreted program is that your code will, one, run immediately. You hit the go button and it goes. It just immediately. But two, and more importantly, affects us a lot more, is when you have an error. If you have an error in your code, it's most likely going to be a runtime error, meaning line 1 runs, everything's fine, line 2 runs, everything's fine, line 3 runs, everything's fine, line 4 has an error in it, it tries to interpret line 4, and then can't do it because you have some, like a type mismatch or something, and the program blows up and crashes. I'm using IntelliJ, which is the same thing. It's like PyCharm for Java. It's made by the same people, by JetBrains. So line 4, your program would blow up, as opposed to a compiled program. A compiled program, your entire code, all of your code in all of your files, the entire project is compiled, meaning it's converted, it's rewritten into another language, and then that language is then eventually interpreted when it's finally time to execute. But your whole program is ran through the compiler first. So the two features of this is when you hit the go button, it's not just going to go. There's going to be the whole compilation process first, which can sometimes take a hot minute. And two, if you have an error, it's more likely going to be a compiler error, meaning there was some problem with the translation process of translating the code into another language, and that process broke down because you had an error. Like if you have a type error in a compiled language, the compiler is going to yell at you. If you have a type error in an interpreted language, the program crashes. Two very different behaviors. So you're usually going to have compiler errors. You can still get runtime errors. It's still very possible, and some of you will see them. Probably most of you or all of them, you will see them at one point during the semester. But they're much more rare in compiled languages. The reason I'm talking about this now is Python was interpreted and Java is compiled. So your Java code is never actually executed. It's compiled into another language called Java bytecode, which runs on the Java Virtual Machine, or JVM, or just Java. If you've ever seen the pop-ups or anything that said your Java's out of date, you have to update your Java, which I don't think those appear anymore. I think it all auto-updates in the background now. But you have Java installed on your device. It's installed on pretty much every device out there. And every device with Java, the JVM installed, can run your Java bytecode after it's compiled. So it makes Java very portable, very easy to run Java on any machine. You've ran millions of lines of Java code in your life and never even had to think about it or care about it. But a lot of your programs are written in Java, and it just runs because you have the JVM. You have Java installed on your device. So when you run Java code, when I hit run, it did work. Except I messed it up. Oh, because I wrote that example line and then delete it. Let me just delete one of these. So when I run my code, I'm going to see progress bars down here on the bottom. This is the compilation process doing its thing. This is all the compilation that needs to be done to translate my code. So it's not an immediate, you hit the button and it goes like Python did. In Python, you hit the button and it just ran. But that's not true this semester. Sometimes you have these long delays when you run your program, and that's the compiler doing its thing. And the compiler doing its thing is a good thing. It might not always feel like it, but the compiler's there to have our backs. It's going to let us know if we have errors before they become runtime errors, because runtime errors are scary. We don't want our programs crashing. We want our programs running just fine. So the compiler's looking over all of our code and saying, hey, I think we have an issue over here. You really got to fix this so your program doesn't explode when you release it to users. We don't want that happening. So the compiler really has our back and does a lot for us to make sure we have less buggy code. Once we run it once, if I don't change any code here and I run this again, it does just run as though it were interpreted, because it is at that point. It doesn't have to recompute the Java bytecode because it doesn't detect any changes. But you usually don't see that when you're working on your code. Usually you're editing your code and then running it again. You're not going to run it again without editing anything. So, but it will run fast if you run it twice in a row, because it doesn't have to recompile. All right. With all that, so that's just my brief. There's tons more to say about compilation versus interpretation, but that's all we're talking about today. Actually, that's all I'm talking about in 116 at all. All right, so let's do some code. Let's call this example code. That's got to be the worst. That's got to be the worst class name ever. And with testing, I usually don't write all my testing stuff each time. I write it once and then copy and paste it all the time. Now that I did it once in lecture, I'm just going to copy and paste that, just so I don't have to do my imports every single time. This I don't need. This I'm not going to need. These I can collapse. Why did that get rid of my wildcard? And these I don't need. In this, let's test some strings. So I want to write some code, and I know I kept harping on writing tests first, but I am actually going to write the code first for these examples. So I can talk about testing, we'll get the code out of the way so we can talk about the testing. That's our goal here. So let's do public. I want to write a method that concatenates two strings together. I'm going to skip the Java docs on this one. It's a straightforward method. It's going to be static. I want to write a method that's going to concatenate two strings together separated by a space. So static returns a string. I'll call it concat. It's going to take two strings, string A, string B, and it's going to return those two strings concatenated together separated by a space. There's my method. It's done. That's it. Just like the add 5, we're going to see a couple of really simple, straightforward methods. I'm going to test this thing, test string concat. These two files are in the same package, so I don't have to import the other one. For your problem set, you do have to import problem set because the tests are in the test package, the problem set's in the other package. So you do have to import there. I don't have to import here because they're in the same package is the difference. And I want to set this up, string A equals hello, string B equals world, because where would we be without hello world, string expected equals hello world. You can check my math on that one. And I want to assert true that these are the same. So my expected, let's set this up the full way. My actual equals example code dot concat a b, and I want to assert that expected equals actual. Okay, so I got a beautiful test case. I'm making sure that it concatenates hello and world. I don't think I have any typos in here. And my code does look fine. A space B, no tricks there. And then let's run this thing, watch it pass. and it fails. Assertion error, example test. Okay. So let me get a hint text. I want to know what the actual was, because what if it's not what I expected? What is it? And it's hello world. So it returned hello world. I'm asserting that it's equal to hello world, but the test is failing. Okay. Let's think about that for a bit. Why is this failing? And I'm actually going to do some debugger here. I think that'll be the best way to show this. Since I don't have my slides to give all the demos, I'm doing the live coding style here. So let's do this in the debugger. So the problem with this is going to be with this equal equal operator. We have to really think what equal equal does. And what it does is checks if the left hand side is equal to the right hand side. That might sound obvious, but we need to think about what expected and actual actually store. What are their values? What are the values of expected and actual? And we might think, whoa, expected, even the debugger doesn't really help me here. We might think expected equals hello world and actual equals hello world. Those are the values of the strings, but the values of expected and actual, since string is a capital letter, oh, that's a little confusing. Every capital letter type in Java is going to be stored by reference. So what expected and actual actually store are references to objects on the heap. Now it's extra confusing with strings because when we do our memory diagrams, we pretend that strings are stored as values, that expected and actual actually do store the strings hello space world. That's the way we pretend that they work in our memory diagrams. But in reality, in Java especially, strings are really weird. Strings behave extremely weird. And we have to treat them a little differently. We have to do something a little special with these things. So what strings actually are references. Expected and actual do store references. That's the value of actual, is a reference to a string on the heap. Expected is a reference to a string on the heap. And what equal equal is doing is checking if left-hand side equals right-hand side. Left-hand side's a reference, right-hand side's a reference. And we can look at the stack here and see that expected is a reference to some string that's a byte array and some magical weirdness. But we can see this at. When we see these at symbols in our memory, in our debugger, did I mention this before? Debugger is showing us all the same information that we do in the memory diagrams. So all that same information, stack and heap, is here. Here's the stack that we went through last time. Oh, goodness. That we went through last time. And each stack frame, we're seeing all the variables that are on the stack. And whenever we have an arrow next to one of those variables, that means this variable stores a reference to the heap, and the arrow takes us to a location on the heap. So we can go to that location on the heap, and we see this at 1384, which is weird because there should be an at for the string too, but strings are weird in Java. Everything's weird about them. At 1384, and the other string, actual, is at 1385. So we have different references. These ats can be read similar to the OXs in our memory diagrams. This is something that is an indication of where this thing lives on the heap. It's not a literal location, but it is an identifier for that object. And what it's important here is that these are two different objects. 1384 and 1385, those are not the same references. Therefore, these are not the same values. Therefore, this should resolve to false, even though both those objects both have the exact same values, hello space world. It doesn't matter. Equal equal is checking the values of the variables. The values of those variables are references to objects. So this correctly fails. If we change this, here's where strings get really weird. And doing a string literal like this is kind of like saying new string. Just like saying new array list, it's similar to that. But strings are weird. So now these two strings, hello world and hello world, now they're actually the same string, which is extra weird. And if we run the debugger again, we can verify that. 1363, 1363. So now they're the same string. I'm telling you, strings are weird. So what we're going to do about this, so this test fails. What we're going to do about this is never, ever, ever use equal, equal to compare two strings in Java and in a lot of different languages, but especially Java has this feature, is we're never going to use equal, equal. We're going to use dot equals. The dot equals method is going to check the values of the objects themselves, not the references that are stored by the variables. This is going to go to expected and actual on the heap and go through character for character and check if they refer to strings that have the same sequence of characters, which is pretty much always what we want. It's always going to be what we want. We don't want to say, do these two string variables refer to the same string, because strings are weird. It's not going to be valuable or helpful to us. So we don't want to do that. But now, with dot equals, even though these are two different strings with the same values, we're going to get our test passing because equals is going to do that check for us. If we go into the equals, we can kind of see, I mean, the code isn't exactly legible, but we can go through here and eventually find where it's going string, character for character. It's iterating over the length of the string and making sure, it does check if they're referring to the same string, just shortcut everything and oh, sorry, I'm reading that wrong. If the lengths are the same, I think I skipped over that part already. If the lengths are the same, then go through every character in one and make sure that it's equal to the character in the other. So it's checking character for character, is this exactly this string that we're looking for. Here's where it did the reference check. If they're referring to the same string, just return true right away. There's nothing else to do. But if they're both strings, then go character for character and return true if all of the characters match and false if any of them don't match. So this is the behavior that we want, but there's a lot of code that goes into that equals method, all the stuff we just looked at, that is going to do what we want it to do. So always use dot equals, not equal equal, when comparing two strings for equality. That's the takeaway. That's what we want to do. And if we do assert equals, assert equals, let me get these in the right order. Let's get these backwards. I'm going to try to be better about that. Assert equals will do the same thing. So this still passes. So if you're comparing two strings for equality in a unit test, you can use assert equals, and that will still call dot equals. We can do the same thing. By the way, I'm doing control click on a method or command click on Mac. I'm going to click on the method, and that's going to take me to its definition. So if you're ever interested in the source code or just quickly jumping to a method definition, that's going to get you there real quick. So assert equals is going to call assert equals. We're just going to call assert regarding null, and eventually in here, if they're both strings and actual instance of string, throw new comparison failure. Fail not equals. Oh, fail not equals. Yeah, we want this. Fail format. Why am I struggling on this one? Just get me there. Assert equals. I think this is the one we want then. Assert regarding null. We're just going to call is equals, which finally, now that I dug in the right spot, once we get a few layers down of null checks and a bunch of other stuff I don't want to talk about today unless somebody asks. If you're interested in that, but it would be a side quest. And once we get down to what's actually happening, it is calling dot equals on the two objects. It's not using equal equal in here. It's using dot equals as long as it determines that both of the things that we gave that are references to objects, it's going to call dot equals on those two objects. So assert equals is calling dot equals. There's no magic there. It's just calling dot equals with some extra checks that we're not really interested in at this point. So it is doing the same thing. And sometimes, remember, assert true is your sledgehammer. That's always going to work for you. It's tried and true. It's always going to do what you need. Assert equals isn't. So when so assert equals will do your strings just fine if you're expecting a specific value. But when you're expecting two different values, you still got to pull out your assert true. Oh, because we're in assert equals. Oh, yeah, and that was my hint text. Oops. So we still got to pull out assert true when we need two different values. That's where we're going to do our assert true and then an or. So sometimes you do have to remember to call dot equals. You can't just be dependent on assert equals. And especially when you're writing code, like when you're writing tests, that's one thing. But when you're writing the actual code and you have a conditional, if some Boolean expression do something, you're not going to have assert equals available to you because it's not in a JUnit test class. So that's when you're going to have to use dot equals as well. Okay, so that's comparing strings. Your TLDR is never use equal equal to compare two strings. The only time you're actually using equal equal in Java is to compare two ints. It's the only time it's really useful. In 116. There are other cases. There are other types like longs, bytes, shorts, but those are all integer types. So the same is still true. And two Booleans, if you ever want to check if two Booleans are equal instead of just asserting if it's true or false. Few rare cases. For our purposes in 116, it's only ever comparing two ints that you're going to use equal equal. Or any of those comparisons. Which is fairly often. Like loops, when we're looping over the indices of an array list, we use less than equal, less than. We can use those comparators. But any other time, nope. That equals in this case. Okay, so let's write another method. Oh no, I almost skipped the whole thing. The other thing. So let's write some code. We need to. Let's jump to this code. We'll revisit this. What are. No, I have to talk about that. I'm like, what is the point of this example? I always go through it because it's in my slides, but I gotta think about what I actually want to talk about with this example. But yeah, let's do it. String. So I want to expand on this example and do a method called plus minus, which is going to take the same score and return a plus return plus if the score should have a plus. Let's do it by example. That's the way I do it in my slides. Example 87 to 89 is a B plus. So we want to just get that plus or minus. Let's say 83 to 86 is a B. And 80 to 82 would be a B minus. So this should return plus return empty string, return minus. So that's our expected behavior, and we're going to get a little fancy with it. We're going to say int ones equals score modulo 10. So this is going to take just the remainder of the division. So it should get us just the ones digit here. And then if ones greater than equal to 7, we're going to return plus. Else if ones greater than equal to 3, return empty string. Else ones must be less than 3, so we're going to return minus. So that's our method, and we're here today for testing, so let's write test cases for this thing. So my next test public void test plus minus. That was in the class called plus minus. It doesn't even make sense when the first time we visit that example there's no plus minus. So plus minus from week1.lecture, the one that we just wrote, and the plus minus method, and let's do 87. So string result equals plus minus of 87, and we're going to assert, I'm going to use my assert equals here. Yeah, that was this lecture. I talked about the autocomplete thing. I didn't talk about it in the other one because I teach off the slides. I expect this to be plus. I'm going to duplicate this a couple of times. Let's just do 3 test cases, 80, 84 should be empty string, and 71 should be minus. Now this isn't going to be a full test class. What I'm doing here is just showing the start of a test class, and often I'll do that in lecture just in the interest of time. We don't have time to write the whole test suite, but I would want to test a whole bunch of different inputs on this. And by the way, this method is going to have lots of issues. There are a lot of problems with this method. We're going to talk about one of them today, but the intent is to set this up for a future lecture where we fix all of the issues with it. We're probably not going to get to that lecture. It's the day of the midterm, and I just won't have a ton of time that day because the midterm takes up most of it. And I got to talk about file I/O. So I don't know if we'll ever visit it, so I just want to talk about them now. Both of these methods, the one we wrote earlier for letter grades and the plus minus one, neither of them handle invalid inputs at all. So if you give it a score of a negative value or anything over 100, you're just going to get wacky results. Anything over 100 is going to get an A, sure, that's fine. But anybody with a 131, for example, is going to get an A minus, which they're going to be pretty mad about that. If somebody has an 8 in the course, or a 9, we'll give them a 9. Somebody has a 9 out of 100, they're going to get an F plus. But if they had an 11, they would have an F minus. So that's kind of weird too. So the plus minus should check for the range of 60 to 100, and letters should check for the range of, well, I guess it could do 60 to 100 still, but 0 to 100 to make sure the inputs are valid, and then that'll get rid of your F minuses and F pluses, and any invalid inputs. And on invalid inputs, there would be a special string. When I do revisit it, I return the string invalid input on those cases. Okay, So here's our tests. Let's run just these tests. We don't need to run our string concat tests. And we pass. Cool. And we're feeling good. We wrote some tests. Those tests fit. Those tests pass. We're feeling good about our code. But just for fun, let's add another test case. Let's check that student who got 100. They should get an A+ in the course. Let's run this test again. And they don't. We expected plus, but we got minus. That student with 100 who demanded perfection and held themselves to a perfect status all semester ended up with an A- because our code isn't perfect. So this is where we want to make sure we pass on every test case. In this situation, 100 is actually one of our edge cases. Edge cases aren't always 0, empty string, empty array, list, empty hash map. They can be problem specific. You got to think about what inputs are very special to your specific problem. In this case, 100 is a special case. It's not going to fit the logic of our plus minus because it's going to fall into the 0 while the ones digit is a 0. So we got to go into the else and return a minus. This is a situation where our edge case, which is often the situation, our edge case is going to need a special conditional. So if score equals 100, these are ints, so equal is what we can use, return plus. So if it's 100, just treat that as a special case because it's not going to fit the logic of how we're handling this over here. It's not going to fit this, and we want to do this because we don't want to have to write every single range. If it's between 87 and 89, if it's between 77 and 79, if it's between 67 and 69, if it's between 97 and 99, we don't want to have to write all that crap down here. And the same for minuses and everything. We want to be able to do this because it cleans up the code a significant amount. But 100 has to be handled specially because it doesn't fit this structure. So we're just going to handle it as a true edge case. If it's the edge case, do one thing. If it's not the edge case, do the rest of the thing. And since I'm using a return statement, I don't have to have an else. I could add an else and put everything else in the else block. But since this returns, it's effectively doing the same logic, same pass through the method. Okay, now we can run our tests again. And here I'm in one file, but running a different one. So I often want to do that. Now we do pass. And that's what we need. This student with 100 demanded perfection, and so do we. We need to pass every single test case. Because there's a temptation. You can say, well, there's 4 test cases. 3 of them pass. That's a 75. That's enough to pass. Like that's going to be a C. I'm good with that, right? No, we're not good with that. That's dangerous. What am I trying to say? So we could just add enough test cases. We can add a whole bunch of more test cases here and fail one to the point where we're getting 99%. Because we are correct on 99% of the valid inputs here. And we're going to walk away with our A+. But then that student who got 100 walking away with an A- isn't going to be so thrilled with us saying 99's an A+. Who cares if I didn't get everything? No, we need to be perfect. We can't have bugs like that. If you have a bug that's happening 1% of the time for your users, 1% of the time, depending on the exact application and everything, 1% of the time might mean every single user is experiencing a bug every couple minutes, depending on how often that method is executed. We can't have any bugs, especially if a bug results in a crash. In this situation, a student got the wrong grade. That's not a mistake I can make. That's going to be an immediate email from that student, as it should be. Immediate email telling me to fix my shit because my grade book's busted at that point. Can't make these mistakes. Can't make any mistakes in our code. Demand perfection. And let's revisit this. Make sure I forgot and had to tack it on to the end of the first lecture. This code, can't even get them both on the screen. This code uses integer division by 10, which we did last time, and then modulo 10 today. This one's specifically designed to help you with sum of digits. If you're struggling working on sum of digits for task 1, This is the big hint. I dropped little hints last week. I think I forgot to give a bigger one in this lecture last week, but here it is right now. Is if you combine these two ideas into the sum of digits, you can get the sum of digits real quick, real easy. So what you want to do, what you can do, you can do it any way you want, any way that works. But this is my recommended way. I think the simplest way is you take the value, the input modulo 10, that's going to give you just the ones digit of the input, and then store that in your accumulator variable, add that up, and then do integer division by 10, which is effectively going to erase the ones digit or shift all the digits to the right by 1. Now the new ones digit is the old tens digit, so you can do modulo 10 again to get the value of the original tens digit, which is now the ones digit. So you can get that digit and then add that to your accumulator, divide by 10 again, do modulo 10 to get the hundreds digit, the original hundreds digit, divide by 10, get the next digit, divide by 10, get the next digit, and keep doing this until your value is 0. That's when there's nothing left to read at that point, you're done. And then your accumulator should have the sum of all of the digits at that point. So combining these two things, that's why I have this example to lead you to getting that. Because without any hints, sum of digits is pretty tricky. But with that hint, it should be easier because I want you to focus on task 1 especially. I want you to focus on Java syntax and writing your first unit tests. I don't want you struggling too hard to just write the code itself. The code shouldn't be too tricky. So there's your hint to make sum of digits straightforward. And then everything else is 115 concepts except unit testing, and then applying it with Java. Okay, if there are questions, I'm not going to, usually during a live lecture, I'll stop for questions so people can do the old raise their hand and stuff. I'm not going to stop for questions in live lecture because we have, or in streaming lecture because we have chat. So if there are ever any questions, just hit me up in chat, and once I'm at the next end of my next sentence or example or whatever, I'll get to your question in chat and answer it there. Okay. With all of that, and these days are long, it's 2.5 hour lectures, almost back to back. There's a half-hour break between. It's just a lot of lecturing. I'm 4.5 hours in, starting at 8 a.m. But we're doing it. I'm still going strong. So let's shift to the next example. Oh, we do got it up though. So no. Yes. 29 dropped frames. Okay. Seems to be back. I think my internet had an issue there. Okay. I think we're good. Looks like I lagged a bit there. Hopefully that's not a common thing. So what I want to do is something. So we did ints, we did strings. Let's do doubles now. Let's write a very simple double method. I want to do multiply by 3. Just like we did add 5, I want to do multiply by 3. And then double input. Simple method. Look at me go. Pro coder here. Input times 3.0. Beautiful. Man, I love that method. Whew, look at that method. That's awesome. All right, let's test it. I think it's right, but you know what? Let's test it just to be sure. That's what we're here for. Today is testing public void test. What do you mean YouTube is not responding? Streams live still. Test multiply and double x equals, let's do 0.1, and then y double y equals multiply example code dot multiply by 3x, and then double expected equals 0.3. If I know my math right, 0.1 times 3 is 0.3. Then assert, let's do assert equals. Oh, we learned assert equals for a reason. Expected and y. So y should be 0.3. Okay, there's my beautiful test to test my beautiful code. Let's run this. What could possibly go wrong, right? Everything's so straightforward here. There's no way that test failed. Oh, that test failed. Well, crap. Assertion error. And it's giving me a strange thing here. So let's go back to the basics. Let's do assert true, expected equal y. Let's run this. Assertion error. Okay, well, if y isn't 0.3, then what is it? Let's add y as our hint text. Oh, I forgot this again. String dot value of will convert to a string for you, a primitive to a string. So let's use y as hint text, or you can just do like any string concatenate, and then the concatenation operator will convert it for you. So sometimes you'll see things like this, empty string plus, just to convert a primitive value to a string. This is actually comes up in a later lecture exam. Oh, I'll live code it, so I don't have to do that in this lecture though. But that'll get y as a string. So let's see what y is. If it isn't 0.3, what could it possibly be? Well, it's 0.3, 0, 0, 0, 0, 0, 0, 0, a bunch of zeros, and then a 4. Well, Java's right. That's not equal 0.3. So we still have an issue here, but unlike with strings we looked at the values and we're like, those are the same value. Like, what the hell? And then we had some weird reference thing. With doubles, we actually don't have the same value. This is not equal to 0.3. So what went wrong? What happened here? Because something happened. Something was wrong. And I'm pretty sure my math's right. I just did 0.1. In fact, we don't even need a method call for this. If I just do 0.1 times 3.0, we're going to get the same thing. Doesn't even have to be in a method call. I'll keep it as a method call because when we're writing unit tests, we're usually testing methods. So what's the problem? Well, to understand this, we have to learn a little bit about binary and how doubles are represented in the code. Is there anything I can't get to any documentation. I didn't think so, but I had to try. Actually, maybe I can go to the double class. Neighbor class, blah, blah, blah. Raw long bits. Hey, look at this cool stuff. Hey, this is actually, this is like exactly my lecture example. They stole my example. People are going to accuse me from stealing it from here. Maybe I did steal it from here and forgot where I got it from. But yeah, this is what I'm gonna say. Yeah, there's good stuff. It's good stuff there. Part of that's what I'm gonna say. I'm still using the same exact examples. Fuck it. But the problem here is how doubles are represented in our code, in our programs. And doubles are represented the same way in I want to say most, but can I just say all? I'll say most to hedge my bets. Most programming languages, they're all representing doubles in the same way, which is our IEEE format, which is a 1-bit sign. It's a 64-bit representation. 64-bit representation. It's 1 bit for the sign. It's 11 bits of exponent and it's 54 if my math is right. 52. Oops. 52-bit mantissa. I don't think it's even spelled right. I won't use the fancy word. Bit fraction. And what this is scientific notation. So we have, why is that not lining up? So we have 1 point the fraction value times 2 raised to the exponent. Then I guess the sign is out here. So it's effectively scientific notation, but in binary. So we have 1 point the fraction raised times 2 to the exponent. With scientific notation, you have 10 to the exponent would be the big difference. But here it's all in binary. And the key takeaway for us in 116, why is it adding the extra space there, is that 52 is a finite number. So in decimal, we have values like 1/3 that we, which is not equal to 0.333. No matter how many threes I type here, those values are not equal to each other. Threes have to repeat out to infinity to be able to get those two values to be equal to each other. In binary, we do the same thing. If we want to represent a value in binary, a fraction in binary. So first, let's quickly go over binary. I'm not going to talk about binary values too much. I guess I could. Let's do 110. In binary, this is going to convert to, so we have the, like in decimal, we would have the ones digit, the tens digit, the hundreds digit. In binary, we have the ones digit, the twos digit, and the fours digit. So we do the same thing, except we have powers of 2 instead of powers of 4. So this is 4 plus 2 equals 6. So this in binary is 6 in decimal. What you probably haven't seen before is the other side of that. Is on the decimal portion, it does the same thing. In decimal, in base 10, it's tenths, hundredths, thousandths, hundred thousandths, or tens of thousandths. Is the same thing for the decimal portion in binary, except it's base 2, so it's halves, quarters, eighths. So this value is going to be 1/2 plus 1/8. And we have a 0 for the 1/4 digit, so we don't have a 1/4. So this is 5/8 for this value. Where the problem comes in is when we have values like 0.1 in base 10 convert to in binary. Oh, I'm going to get my value wrong, ain't I? 0.00011. 0.011. Right, this is half, quarter, eighth, 16ths. Yeah. Oh, yeah. Hey, I did get it right. 16ths. Okay, and then 0011, 0011, 0011. So 0.1 in base 10 cannot be represented exactly as a binary value. It's going to repeat 0011 forever, out to infinity. And since infinity is greater than 52, we only get the first 52 bits of this. Now it's scientific notation, so the decimal will move right here. And then we get 52 ones and zeros, not infinity ones and zeros. We get 52 wherever 52 is. I'm not going to count them. But we get 52 of these ones and zeros, and then our exponent is -4. And that's our value. So everything after 52 is truncated, is deleted. So the way we represent doubles, we cannot represent certain values, 0.1 being one of them. That's why I chose 0.1 for the example. This 0.1 cannot be represented in this IEEE double format, which all programming languages use sure there's one language out there, just to force me to say most, that doesn't use it. Any language that's worth talking about uses this, and it can't represent these values directly. So 0.1, this is not actually 0.1 when it's stored in this double because it can't fit. There's not enough space in these 64 bits to be able to represent the entire value exactly. So it has to be an estimation. It's a rounded value. So we have this rounding error or truncation error when we represent our doubles in binary format. And sometimes that doesn't really matter. Like if we print out x to the screen, it's just going to print 0.1. Everything's fine with that. It just prints 0.1. But once we start doing some math and doing some computation with these approximated values, then those truncation errors can compound and start showing up in our code. So that's why this y, after it was 0.1 multiplied by 3, is different than just straight up 0.3, which is represented a little bit different, still truncated, but represented in a different way, where y ends up with this trailing 4 way at the end here, and this 0.3 didn't. So that's why. That's the why. It's because doubles aren't represented exactly. So what do we do about it? And the answer is almost the same as it starts off at least, almost the same as our conversation about comparing strings, is never, ever, 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 ever use equal to compare two doubles for equality, at least in Java. Some languages have the equal do the thing that we're about to talk about. So that's a little different in Java for sure. Never use equal to compare two doubles. And we can't use a dot equals either here. What we're going to have to do is write our own helper method. I guess I'll write it out of order. Usually I'd have my helper methods at the top, but just for the sake of organizing this. What I want is a helper method, which I can make private. You know what? I don't want to talk about private yet. In the slides, I have a constant and private and stuff we don't really have time in this lecture for. I jammed a lot of stuff in that lecture. I'll save a lot of that for Thursday in this lecture. So public void compare doubles, which is going to take two doubles, double A, double B. And what I want to do is check not if these two doubles are equal to each other, and I'm actually going to use an assert true here. Not if these things are equal to each other. So one, you can have helper methods that have asserts in them. This can help, especially when you're writing your utility methods from task 2 onward. You can have asserts right in your helper methods. I'm not annotating this with a test, but I'm going to call it from my test. So instead of assert true here, we're going to get rid of this garbage and do compare doubles x, y. And we're not going to check these doubles for equality, but we're going to say, are these two doubles close enough to each other? So I'm going to check if the absolute value of the difference, so the magnitude of the difference, is that less than some small value? If it is, then we good. So I'm checking, is the absolute value of the difference, the magnitude of the difference, less than some small value? The choice for that small value depends on your specific application. For 116, if you use 0.001 for all applications, all the assignments, all the programming tasks, you'll be fine. So if you stick with 001 or even 0001 will be fine. If you have too many zeros, then the truncation errors can be larger than what you're comparing. So you want this to be large enough that it will allow for truncation errors, but not so large that it's going to interfere with the logic of our program. So if we have like 0.1, you can have pretty wrong answers that are going to be accepted in your code. So what we're saying here is if A and B are within 0.001 of each other, we're going to call that close enough. It's enough to get rid of all my truncation errors, but not so different. Like if they're within 0.001, I'm going to call those pretty much the same, and we're going to be good with that. So now we run this with compare doubles, and we fail because I used x instead of y in expected. But hey, we got to see our test fail. I always like to see my tests fail. Make sure they're testing something so we know it is actually testing something. And then we get our passing test. So now we're saying, okay, expected and y are at least within 0.001 of each other, and that's good enough for us. So we can use assert true, or assert true for that. Assert true, again, is your sledgehammer. It's always going to be handy. It's always going to be there when you need it and do whatever you need it to do. Assert true can do everything. But sometimes we do want to be a little, make things a little easier on ourselves. So we can use assert equals to compare two doubles, expected and y. Except with assert equals, it takes a third argument, which is going to be that tolerance. So if we do 0.001, assert equals with doubles, it's going to do the same thing that we're doing here. So we got both of these passing. It'll do the same thing. Let's see if I can verify this. I don't know if I've dug into this one, but it should be doing the same thing as we're doing right here. Math.absolute value of the difference, less than, they do less than and equals, but the whole point of doing this is that doubles aren't going to be equal with any reliability. So I'll do strictly less than delta. I suppose if somebody gives a delta of 0, they want it to pass. So I guess that makes sense. But it's doing the same exact thing that we're doing, just with a few extra checks as usual. But same exact thing. So it cleans up the code a little bit. You don't have to have your helper method and everything. But if you're writing code where you need to check in a conditional if two doubles are equal, in your code you're not going to have access to the asserts. So sometimes you will have to use this logic to be able to do this thing here. That's comparing doubles. Never compare two doubles with equal. It's an easy way to write broken code in the context of 116. It's an easy way to get Autolab to not give you points. This is your test average is exposing this one, is assessing you on this. Test average, it returns a double. Oh, I don't want one drive. It returns a double. Make sure you're not checking that for equality. Okay, and oh my goodness, it's only 8 minutes. And we got to talk about recursion. We didn't even get to recursion. What do I call it? First recursion, right? I'm just going to call it recursion here. Let's write some recursion. And for this, I'm just going to do a main method. Public static int add. I'm just going to add, sticking with our theme, add two numbers, int a, int b. Return 0. I'll stub it out. Let's get our test here. Our test just in a main method because we want to see this in the tracing tool eventually. So int result equals add of 4 and 3. S out result. So that's our I guess test case. Now let's write some actual code to handle this, and I'm going to write a recursive method. So I'm not going to explain too much here because I'll explain it in the memory diagram, but I'm going to check if b. I'm not going to explain much of y because how this could be half a semester just on recursion. But if b equals 0, I'm going to return a. So if I'm adding a plus 0, the result is just going to be a. Else, if I'm gonna skip in the example in the slides and in the repo, I write this in a way that handles negative numbers too, but I'm only giving it a positive input. So this will be broken on negatives, but I'll be fine with that for this example. And then return. So if the value is not 0, I have some actual work to do. I'm going to assume that b is positive, and I'm going to return add. So this method is named add is calling a method named add, which are in fact the same method. This is a method that calls itself. Any method that calls itself is a recursive method. You even get a special symbol on the sidebar to indicate that this is recursive. So add of a plus 1, b minus 1. So that's the method I want. And my claim is that this will return 7. And hell, we can verify that. This should print 7 to the screen. So it does work. But let's figure out why it works through the magic of a memory diagram. In 5 minutes, maybe. That's a quick memory diagram. Maybe I could just walk through this one. No, I actually changed the code a little too. Let's just do it. If I just... Did I not copy that code? Come on. Copy. Paste. There we go. All right, so let's just rip through this. Main. Let's get to the good parts. Let me get through the quick parts. I'm going to start going through the boring part, not the boring parts, the usual parts that we've gone over multiple times. Like right now I'm putting a frame on the stack and assigning the parameters equal to the arguments, the main method, a return value for the variable. Like we've seen all this stuff already. So I'll go quicker. If there are questions, I'll slow down. I can't really slow down today because we're running low on time here. But in most cases, I can explain more. But I'll assume that we're all up to speed on that stuff at this point. So we have 4 and 3. We're ready to run this code. If b equals 0, b does not equal 0. So we're going to go to the else, and we're going to return add of a plus 1, b minus 1. So we're at the recursive call. We're at the good part that we want to talk about today. We're calling add, which is a recursive call to the method that we're currently running. And recursion can get tricky. It's hard to write good recursive methods, and you know, it's just a tricky concept. But when you're doing your traces, it's not that tricky. When you're doing a trace of through memory of a method that's recursive, my trick to this is that there is no trick. You get to the recursive call, just completely forget that it's a recursive call. Don't even worry about it. Just treat it like any other method call you've ever traced before. So I'm just going to treat this like a regular call. Add has a parameters a and b, and they're getting the values a plus 1, b minus 1. The arguments are always evaluated in the current stack frame. We're setting up the next one, but we're still in this stack frame here. So a is still 4. So 4 plus 1 is 5. B minus 1 is 2. And then I run the next stack frame. And I have multiple stacked frames with the same name. That's perfectly fine. We can tell which is which by the parameters. But this stack frame is going to say is b equals 0. No. It gets to the return, the else. Return a new add of a is a plus 1, which is 6, and b, which is b minus 1, which is 1. This stack frame, b is not 0, so we hit the else and do another add stack frame, and we keep adding new stack frames to the stack each time we hit the recursive call. So 7 and 0, and when we get to this recursive call, we get to a very special situation called our base case. So the recursive method just keeps calling itself, but if it kept calling itself forever, nothing's going to end. The program's going to blow up. So eventually we have to get to what's called a base case, which is a situation where the method is called, where it doesn't call itself. It doesn't make a recursive call, and it's just evaluating something and returning. So once b equals 0, we're just returning a, and this stack frame is going to return 7 back to this stack frame. So this stack frame has control again, and it has to remember where it was. It was right here waiting for this to resolve. This resolved to 7, so it's going to return 7 back to this stack frame, which gets the value 7. It was right here waiting for this to return, which returns 7. So it's going to return 7 to this stack frame, which was waiting for this to return. That returns 7. So this is going to return 7 back to the main stack frame, which then prints 7 to the screen. So we had 4 stack frames to be able to do all this, to do this work, to add these two values, which of course you wouldn't write this method, you just do 4 plus 3. But 4 stack frames to get the recursion done. Each stack frame added 1 to A and kept decrementing B to get B closer to 0, the base case. So our recursive calls, we can make recursive calls, but each recursive call should get us closer to the base case. And if we don't, so let's jump, oops, cross out the main stack frame. That's the end of that trace. There's a quick trace. If we don't get closer to the base case, so say B is negative, and then we're decreasing and going more and more negative, we're not getting closer to 0, we're not getting closer to the base case, and what's going to happen is we're going to blow up the program, and by that I mean we're going to get a stack overflow error. This means we kept putting more and more frames on the stack, and eventually we ran out of stack space, we exceeded what the operating system gave us for our program, and our program blew up. And it blew up pretty late. Like, this isn't something we really have to worry about unless we're going infinite with recursion. Because we can see here, we had over 1,000 frames on the stack before we ran out of space. So we have quite a bit of space available to us. You're not going to overflow the stack in any normal operation of any program. You're not going to have a method that calls a method that calls a method 1,000 times. But when you go infinite with recursion, that's where you're going to see stack overflow errors. So this is what happens if you see stack overflow when you're using recursion, you went infinite. So with that, we're out of time. Oh, we're a minute over time. All right, so I'm going to take a quick break, and then I'll, if anybody has questions, I'll see you in office hours in the Zoom meeting. If not, I'll see you in 2 days on Thursday. Don't forget, homework 1 is due Thursday morning, so you really have today and tomorrow. Get that task 1 done. All right, take care, everybody. And I'll see you on Thursday. See you, Nicholas.